Let's read over some of the examples for using the comparison test. In the first example, we have a series where it is defined by a sequence of terms, an. And note that as we're copying this down, we can look and see that there is a highest order term, n to the third. As we're copying down the other terms, they are of smaller value. These are lower order terms compared with this highest order term. So with that thought process, we can then identify a sequence of bn's. And when we make the comparison, we want to look at our an and compare it with the bn and see that the bn's are always bigger than the an's. Since the bn defines a series, which is a p series, p equaling 3, p is 3. What's important about that is that it's bigger than 1. That tells us that the series of bn's will converge. So we need two things. We need 1, the good inequality, and then we need 2 for the series we've cooked up to converge. With 1 and 2, we can then make our conclusion that the given series will converge by CT. Nice. In the second example, 1 over 2 to the n plus 1 is given to us. Again, if we ignore that lower order term, we're able to see 1 over 2 to the n is the same thing as 1/2 raised to the n. And then comparing 1 over 2 to the n plus a little bit is bigger in the bottom than just 2 to the n. Therefore, the reciprocal behaves in the opposite direction. And we can see that, like the previous example, that we have an inequality going in the direction that the an's are smaller than the bn's, and as well that the series we've chosen converges. So with 1 and 2, what do? We get to conclude that our given series will also converge by CT. Okay, so that's two examples where in both cases we concluded convergence. Let's take a look at a case where we use CT to find divergence. In this case, we are given a series where the sequence takes the form of an being the reciprocal of the natural log function. It's convenient to review the natural log function. So let's map out a graph of the natural log function. Before graphing the natural log, let's bring in this convenient curve. The line that goes through the origin and has slope of 1. If we think about x's being 1 and find the corresponding point on this curve, y would also be 1. If we let x equal 2, the corresponding point on the curve would also have a y coordinate of 2. Now what were we going to do? We're going to graph the natural log function. And the natural log function looks something like that. So then the points of interest for us are when x is equal to 1, to 2, to 3, and so forth. And then we're going to let those guys, those y values, be A1, and then A2, and then A3. And then our sequence of A's is the reciprocal of these guys. So obviously, I made a mistake here in copying down. Obviously, we can't take the reciprocal of 0, and that means that over here, our index on the series doesn't start at 1, but actually starts at 2. Okay, so why do we want to look at this? Well, we're going to end up playing with the reciprocal of the identity function as well as the reciprocal of the log function. And then looking at the identity function, it has y values which are always bigger than the logarithmic function. So that nicely says that looking at 1 over the log will be bigger than 1 over the index n. Okay, and what do we have? We have an inequality going in the opposite direction. And then for the series given by these terms, that series diverges. So we have 1 and 2. Therefore, our given series will also diverge. Nice.